Hi and welcome to this Year 2 video from the stats part of the A-Level Maths course, and we're going to look at hypothesis testing and specifically with the normal distribution. So you should have spent some time looking at the normal distribution, you should be familiar with it. With regards to hypothesis testing, you should have seen that before with the binomial distribution in Year 1, and in Year 2 we're looking at it on the normal distribution. So we're going to look at exactly what's going on in terms of kind of means of samples and how they are distributed, and then looking at how sample means can be used to carry out hypothesis tests. So we've got a bit of background work to do first to be able to figure out what's going on with sample means before we actually get to the mechanics of a hypothesis test. So here we go. Let's say we're going to talk about the battery life of a particular phone model, and we know that battery life of this particular model is distributed with a mean of mu hours and a standard deviation of sigma. So there we go, X is distributed normally with mu and sigma squared. Right, now what we're going to do is, let's just imagine taking a sample of 10 of these phones, and we'll call this sample A. And let's take those 10 phones and calculate the mean battery life of those 10 phones. And so that gives us what I'm going to call A bar, the average of those 10 phones. And now what I'm going to do is, I'm going to take another sample of 10 phones. A different sample, I'm going to call this one sample B. And that's going to have a mean of B bar, this thing here. And let's just keep going with this process and keep going with this process. Just like imagine we just keep taking samples of 10, sample of 10, sample of 10, mean of each one, mean of each one. And so what we end up with is a whole bunch of means from each sample. So there's our mean value from our first sample, there's the mean value from our second sample, and so on. And these values here are all going to be slightly different. And what we've done now really is created an entirely new data set in its own right, that is our sample means. And we now need to understand what's going on with this data set here, these values for all our different means. Well, what I'm going to do is say, well, the original distribution was X up here. So what I'm going to do is describe the new distribution of means as being X bar, capital X bar. So that's going to describe how these things here are distributed. And what we know is, there's our original distribution, so X is normally distributed mu sigma squared. And what we find is that X bar is also normally distributed, so those sample means, A bar, B bar, C bar, D bar, all those things, they're going to be slightly different, they're a distribution, and it turns out they are normally distributed. But the interesting thing is that we know from something called central limit theorem, and we don't need to go into any more detail about what's going on with that. It's a given fact that our sample means will have a mean of mu, and they're going to be a lot less spread out. And the measure of their spread, or how spread out they are, is going to be sigma squared over, in this case, 10, which is the sample size. So what you've got is the same mean, but a much, much, much narrower distribution. So I'm going to kind of put those two things on top of each other, and that's what we're looking at. The red one was our original distribution of all the phones, and the blue one is just those the distribution of those individual samples of 10. And I hope that's making some kind of sense. So, what are we saying? Well, the mean of the means is the same as the mean of the original distribution, and take a moment to have a figure out if you're happy with the phrase the mean of the means. And the spread of the means is much, much smaller than the spread of the original distribution. And it's this information that comes from this thing, from this central limit theory, this fact that this here is a known fact about the sample means, and that's what we're going to be using to determine whether or not our hypothesis is going to be true or not. So that's how we're going to use to test our hypothesis. So let's see how we can use this. So what we've got is mobile phones again, and we're told they're modeled with a normal distribution. It's got a standard deviation of 7.5 hours, and your manufacturer's claiming the mean lifespan of 50 hours. What then happens is, so we're going to test that claim of 50 hours by taking a sample, and a sample of 20 batteries are tested, and it turns out the average lifespan for that particular sample is 47.2 hours. So straight away we're looking at thinking, well, you know, kind of 47.2, the manufacturer's claiming 50 hours. Does that sample size of 47.2 tell us that you know, that claim's not true? So we've got to determine whether or not there's a kind of significant difference between that sample there and the 50 hour that we know for the population. So here we go. Using a 5% level, let's test whether or not the manufacturer is justified in making this claim. So what we've got here is our null hypothesis, which is that our average is 50, our mean average is 50. And our alternate hypothesis is that, in this case, we're looking at whether or not it's less than 50. So we've got H1 with sigma is mu less than 50. So, because we're saying strictly less than, that makes it a one-tail test. And so we know from the distribution of all possible samples of 20, we're going to use this one over here, which is how our sample means are distributed. And in this particular case, we've got our distribution of sample means, which is 50 is our mean, and there we go, we've got standard deviation 7.5, so we've got 7.5 squared over 20. So that's the distribution for our samples of 20 phones. And it looks like that. Now, what we've got to do is say, well, we want to know if our sample would be in the bottom 5% of samples taken, because we're going to do a 5% test. And we need to know kind of would our sample end up in that region there. And if it does, then we can say, okay, there's a significant difference. It's statistically unlikely to have happened, so therefore that claim of 50 hours is not going to be true. So what we do is we reject the manufacturer's claim. So we want to know, like, how likely is it to get a sample size of 47.2 given that our average is 50. So what we're going to do is compare the sample mean from our sample with the distribution of the samples. And so what we need to do, we need to come up with this value here down the bottom of the screen of alpha and see, well, kind of what is our cutoff point? Will our sample end up in that blue area on the graph? So here's our distribution. Our sample means is normally distribute 50, 7.5 squared over 20. And what we've got to work out is what's going to be our value of alpha such that the area, the blue area, is less than 0.5. So we've got to bash those things into the calculator. So we're going to use our inverse normal distribution function in our calculators. Now, one thing we've got to be very careful of, though, is if you have a look at that value there, that is sigma squared. That's the variance, because a normal distribution is defined using the mean and the variance. So what that means is when you enter that into the calculator, you've got to enter your value as sigma being the square root of that value there. So we've got 7.5 squared over 20 all square rooted. So you've got to make sure you're putting in the right value. If you do that correctly and bang it all in, what your calculator tells us your value of alpha is 47.24. Now, what's that telling us? Well, our average from the manufacturer sample is 47.2. That is less than the 47.24. It's only just less, but it is less. So what that means is that sample would be in that blue region down that bottom end of our distribution. So what that tells us is that the 5% level, our sample is in the critical region and is therefore has got less than 5% chance of that happening, so therefore it's statistically unlikely. So our conclusion, therefore, is that we're going to reject H0 and accept H1. There is evidence to suggest the manufacturer's claim of an average lifespan of 50 hours is false. Now, there is another way of going about it, so we could do this slightly the other way around and say what we do would be we calculate the probability of getting a sample mean of less than 47.2. So what's the probability of getting a sample mean of less than 47.2? So again, that's one where we just, rather than using the inverse, we just put it in to our calculator, and the probability of getting less than 47.2 is 0.0475, and then we compare that with our 0.05 level, and again we say it's the probability of getting less than 47.2 is less than 0.05, so again we're rejecting H0 and accepting H1. So we can actually do it either way around. Okay, let's have another example. So we've got the number of babies in a litter of the tailless tenrec. That's these cute little bad boys over here. So it's normally distributed with mean 32 and a standard deviation of 4.7. Now, what has happened here, so we've taken just the tailless tenrecs that live in Madagascar and taken a sample from those guys, and we've got the results, and we're talking about the number of babies per litter. So you can see that these fellas don't have to chuck out a large number of babies. So we've got 6 litters, so there's our data set. I'm going to test at the 2% level whether or not the litters from Madagascar tenrecs is different from tenrecs elsewhere. Okay, so our null hypothesis is that our mean is 32, and then our alternate hypothesis H1 is that in this case the mean is not 32 because we're just saying different, so we're not specifying above or below. So what we've got here is a two-tail test. There's our distribution of all the tailless tenrecs, and there's our distribution of our sample means from the tenrecs, and what we've got is our individual sample taken from our group in Madagascar, our sample of 6, so we need to know what is the value of that mean, and there it is. It's 28.16 recurring. So we want to know, is this value here, where does that fit into this distribution here, and is it, let's say, particularly low? So let's have a look. So the probability that x bar is less than 28.16, so I'm going to do this one just by simply calculating what's the probability that I get an average mean of less than 28.16. So put that into the calculator, and it turns out to be 0.0228. I've now got to compare that to my significance level, and because we're using a significance level of 2%, and therefore it's a two-tailed test, so I'm comparing it to 0.01, so we can see our value from our sample is actually greater than that, which means it's not in the critical region, and so therefore in this particular case we're accepting H0. So we're saying that there's insufficient evidence at the 2% level to suggest that the Madagascan version of tenrecs are different to tenrecs across the world. And there we go.